Hey guys. So, I figured the easiest way to cover DNA replication with you would be just to use a few animations, at least to start. Um, all the base pairing that you've been doing for the past couple of days is now going to come in handy because you're going to see how that base pairing really happens in real time with DNA replication. Now, why would DNA need to make copies of itself? Well, you have to remember cells multiply. They multiply because sometimes old cells die and we need new cells to take its place. So if you think about your skin, you're constantly shedding skin cells. If you didn't build new ones, you'd have a little bit of a problem. So DNA replication has to occur every time new cells have to form. You have to make copies of that DNA first in order for the cells to make copies. So I'm going to take you through this process and point out a few important things that relate to the way that the DNA replication occurs. So we know that DNA is a double helix. Double helix meaning, if you notice at the beginning of this animation, that DNA is double stranded and it's twisted. Well, we call those strands complementary strands because they literally complement each other. They match with each other based on those base pairs. A pairs with T and C pairs with G. DNA is going to be taken apart. And in order for it to be taken apart, you need an enzyme. Now, I'm sure you remember us covering enzymes last week. We talked about how enzymes help speed up a reaction, they become a catalyst. And so, helicase is a very special enzyme that's used to force the hydrogen bonds that are holding those bases together to separate. And so it literally unzips the DNA strand, one DNA base pair at a time. It looks exactly like the process of unzipping a zipper. Okay? Once the unzipping occurs, there are some proteins that come in as the helicase is unzipping the DNA. Those proteins are called primase, and they help to hold the DNA strands apart so that way DNA replication can occur. They sort of pin those pieces back, as you can see in the animation to your right. We also have another enzyme that comes in called DNA polymerase. And that DNA polymerase, its job is to read the DNA bases and make new base pairs to go with it. Um, One of the things that's kind of interesting is you'll notice that there is a name for each of the strands. One of the strands is called a leading strand, and the other one is called a lagging strand. And they mean exactly what you would think. The leading strand is in the lead, the lagging strand falls behind, and there's a reason why. So the leading strand, it's a continuous building of the bases. So that new strand that's being built is continuous. It does not stop. The lagging strand, on the other hand, is built in small sections. And so it takes a little bit longer and it lags behind the other strand. The other thing that I want to point out to you that you might have noticed on some of our DNA strands so far are the numbers 5 and 3. And you notice the little apostrophe behind the 5 and the 3? That means prime. 5 prime and 3 prime are how we refer to the ends of the DNA strands. And so there's something very important for you to know about the 5 prime and the 3 prime. When DNA unzips, it always, always, always builds from 5 to 3. And what that means is if you look at the diagram to the right, you're going to see that that DNA strand that's already there is at the 3 prime, and the new strand being built is the 5 prime strand. The 5 and 3 are opposites, and they go across from each other. Okay, because if you think about the strands of DNA, they're what we call anti-parallel. They're parallel to each other, but in opposite directions. Okay, and so when the new strand is being built, it builds from 5 to 3. Okay, And here's another little diagram just kind of showing you how the DNA polymerase comes in and literally reads each base and begins to put the new base pair with it. Keep in mind that original strand is the old strand. The polymerase is now making a new strand. Now, what's really neat is sometimes there can be mistakes in reading the DNA code. And so, as polymerase is creating its new strand, if there are any mistakes, those mistakes can be checked off a little bit later when the polymerase comes back and does a big check of all of those bases. And so they do have a checkpoint to make sure that it's done correctly. So now that you've got the two strands, all that proofreading occurs, that editing, that checking, making sure that if any pairs are mismatched, they're addressed. Most of the time, those mistakes are caught, but sometimes they're not. And so when we start talking about mutations, genetic mutations, some of them have a lot to do with the wrong base pairs being connected to each other. Keep in mind that this whole process of DNA replication is what we call semi-conservative. Semi-conservative, again, that means that when the DNA strand unzips, that's the two old strands, a new strand will be built with each of the old pieces. And so half of the new strand is the old piece, and half of the new strand is the new piece. And that's why it's semi-conservative. And so these DNA strands are constantly replicating. It's something like 50 base pairs per second can be created. There's an official time on that, but if they could calculate, it's somewhere around 50 base pairs per second that can be built. Not all of our strands of DNA, or each chromosome, I should say, is the same size. So the time to copy an entire chromosome does differ depending on the size of the chromosome. Okay?